So we're back with the videos because last time with the investigation video, I had some really good feedback from everyone, so thank you so much. Since the exam is so soon, I've decided to narrow down the number of topics I'm going to be making videos for. So through popular voting on Instagram polls and things, TrigFunctions was definitely one that came up a lot, so this is the first one I'm going to be making. In this video, I'll be going through the parts of a trig graph, general formulas, what they mean, and probably some practice questions at the end. Note that everything that I'm going through right now is on my PowerPoint that I made at the start of the year, so feel free to check that out. If you have any questions, feel free to DM me or shoot me an email. Firstly, a trig function is any function with sine, cosine, or tan in it basically. Like those are the three that you have to know. So here I've drawn for you 3 samples of trig graphs. Notice that the cosine graph is the same as the sine graph, but horizontally shifted by 90 degrees. With any function, you can write it as AF bx plus c plus d, or AF b in brackets x plus c plus d. Notice that one is just an expanded version of the other, so it's easy to switch between forms. The reason why I've written f is that it's a placeholder for any function. So in this case, f could be sine, or it could be cosine, or could be tan. And same for the other one. Now our goal is to associate each of these letters, A, B, C, and D, with a different property on the trig graph, so we know what changes with what value. First, let's go through the different parts of a trig graph. So here I have a generic sine or cosine graph. The first property I want to draw your attention to is the mean line. The mean line is just the line that runs down the middle of the graph. And in this case, the mean line is y equals 2, because that's the equation of that horizontal line that we created. The next important feature is the amplitude, which is the height from the peak to the mean line, so like this height. And in this case, the height is 3 because, as you can see, the height is 3 units up. The last feature is the period, which is the length between 2 peaks, or it's also known as one wavelength, like this. In this case, the period is 2 pi, as you can see from the coordinates here, and that's the same length as a wavelength. Finally, let's look at some tan graphs. Tan has no amplitude, but it does have asymptotes, which are lines that the function approaches but doesn't touch. These dotted lines are used to denote asymptotes. So if you are ever asked in the exam or test to graph a tan graph, make sure you draw in these dotted lines because they are a feature of a tan graph. The reason why there are asymptotes on a tan graph is because, remember, for some values of tan on our unit circle, it is undefined. Now, initially we said that our aim was to associate each letter A, B, C, and D to a particular feature of the graph, right? So I'm going to go back up now and try and do exactly that. We mentioned before that the general equations was AF bx plus c plus d, or AF b in brackets x plus c plus d. So those were the two general equations that you could have for any function. The amplitude is determined by the letter A in both functions. So if A was like 5, then the height from the mean line to the peak would be 5. Next, let's have a look at D. D is actually like sort of where the mean line is on the y-axis, because a normal sine graph would be like this, kind of. But yeah, when you shift it up, the vertical translation is equal to D. So wherever the mean line is on that y-axis, that is D. Next, let's look at B. In both cases, the general rule for a sine or cosine graph is that the period is equal to 2 pi on b if it's in radians, or 360 on b if it's in degrees. Lastly is c, which is the one that we haven't done yet. C is the horizontal shift, but it's different in both forms. So if you're in the expanded form, which is this one, the horizontal shift to the right will be negative c on b, and this is horizontal translation to the right. Whereas for this form, the horizontal translation is just negative c. I think the horizontal translation to the right is a little bit hard to visualize, so here I have a sample of a graph that has been shifted. Notice that in this graph, the graph has been shifted to the right pi on 2. This is because in this case, x plus c became x minus pi on 2, which means c equals negative pi on 2. So we know negative c is equal to positive pi on 2, which is the horizontal translation to the right. Therefore, it's been moved to the right by pi on 2 units. I think the main thing to remember with the horizontal shift is that they have different letters. Because if it's in the expanded form, then negative c on b is a horizontal translation to the right, and if it's in factorized form, then it's just negative c. So here I have a sample question from my PowerPoint. Find the equation of this trig graph, remembering the following things that we just talked about. So firstly, the mean line is here. We mentioned that a is the amplitude, which is the height from the mean line to the peak of the graph. So like this length. And so we know in this case, a equals 5. So we're done with a. Another really obvious thing that you can tell is that d is the y corner of the mean line, right? So that means d equals 4. Because it's the vertical shift. It's been shifted up by 4 units. Remember how we said that 360 on b is the period? So in this case, the period from one peak to another peak is 180, which means that 360 on b equals 180, so b equals 2. So I'm here on Desmos. This red line is the question, the graph that we're trying to find. So I'm hoping to graph in the values that we do know to find out the horizontal shift that we still have to account for. So let's just sub in y equals, we know that a is 5. Now we're not sure if it's a sine or a cosine graph, but remember the cosine graph is the same as the sine graph but shifted 90 degrees. So I'm just going to try cos and then I'll try sine after. Now we know that b is 2 and we're still looking for c, and then we know it's plus 4 because d is 4. So as you can see, the blue is what we've graphed. If we look at the specific points, notice that to make our blue graph into that red graph, all we have to do is horizontally shift it to the right by pi on 4. So we know that negative c on b equals 2 pi on 4, and hence, because we know that b equals 2, negative c equals pi on 2, which means c equals negative pi on 2. As you can see, they're the same graph now. So that is a possible answer. So let's try sine. And these are also the same graph. So these are the two possible answers that you could have. And once again, the cosine graph is just the same as a sine graph but shifted pi on 2 or 90 degrees. Now we're going to take a look at properties of tan graphs. So unlike the cosine and sine graphs, the period of a tan graph is 180 over b, or in radians, pi over b. That's the period. However, it is similar in the sense that in the general formula, AF bx plus c plus d, d is still the vertical shift, and negative c on b is the right shift. In a normal tan graph, the first asymptote is 90 degrees because tan of x, if you graph it, the period is 180. So in a way, you can say that the first asymptote is going to be half of the period if there is no horizontal shift or anything like that happening. So let's try example 2 question. So let's try question 2, which is a question about a tan graph. Firstly, observe that there are no translations evident. Nothing has been shifted, and even if it has been shifted and it doesn't look like it, it's still the same graph because it starts on 0 and it sort of has the same shape and everything. So no translations. The period, as we established before, is 180 over b. And in this case, the period is 360 degrees. So we know 180 over b equals 360, which means b equals a half. So in our generic formula, A tan bx plus c plus d, we've established that b is a half. There was no horizontal translation or vertical translation, so both c and d are 0. So now we're just left with a tan half x. In the test, usually a will equal to 1, because if it's another number, then it's a bit harder. But just to be sure, you can check by subbing in a point or using this sort of handy trick. What you do, you take a quarter of the tan graph. So we know that this bit, right, is half a tan graph. So take the middle of it, like here, this point. And then we're going to do the same here. So we know that this bit is half a tan graph, so just take half of that. And then this is also half a tan graph, so take half of that. And here. So just put dots there. Now, observe the height of it. In this case, the height is exactly 1, right? And that's just a simple trick to find the value of a. So if this point was up here, then a would be equal to 5. I think a major limitation of this trick is that if it's been vertically translated up or down, that might make it a bit harder to do. It's just that this one hasn't been translated, so it's a bit easier to do it on. But the same rule applies for if it's been dilated or anything. And that's the end of trig graphs.